Greetings, folks. Probably the most efficient way to determine whether you actually truly understand a physics concept or an analytical approach that has grown out of a physics concept is to attempt to use the approach to analyze a situation that is relatively difficult. You're about to run into a kinematics problem that is challenging. Let's see how you do with it.
So we have a 3-meter tall elevator that's moving at 2 meters per second upward. There's a bolt in the ceiling which releases and free falls for a period of time, ultimately hitting the floor. So the question is, how far has the elevator moved during the bolt's free fall? Pause this, think about it, see if you can come up with a solution. Pause it now. Okay, so I'm assuming you're back. Let's see how you did. First thing to notice is that there are two independent questions here, and that there are parameters that are common to both. Whether you notice that or not, though, you always want to start with the protocol. And what does the protocol require? You begin with a sketch, which we have. You want to put on the sketch an independent coordinate axis. And you want to include on that axis the appropriate parameters, velocities, positions, etc. Now, you can put this coordinate axis anywhere you want. So as an example, you may decide that at t equal to 0, you'd like the floor to be at y equal to 1. So here's a coordinate axis that does that. Here's the origin. The floor is at y equal to 1. That means the bolt initially is going to be at y equal to 4. This is what the situation would look like at t equal to 0. Obviously, as time proceeds, the elevator and the bolt would be moving upward. But the axis would stay fixed. In this problem, we're trying to figure out how far the elevator rises while the bolt is falling, which means we have to pick a point on the elevator to track. I'm going to track the floor. I'm going to start the clock at t equal to 0 just as the bolt comes loose. And I want the elevator's floor to be passing the x-axis at that point. That means that if the coordinate axis looks like this, the elevator and bolt system will look like this at t equal to 0. That additionally means that the elevator floor's initial position is y1 equal to 0. The bolt's initial position is y2 equal to 3 meters. And to be complete, the velocity of the elevator and the bolt initially is going to be 2 meters per second. This is what the system is going to look like at t equal to 0. So I said earlier that there are actually two problems wrapped up in this situation. What are they? The first is a bolt that is moving upward with 2 meters per second. It's attached to the elevator, so that's its initial velocity. That, once it becomes free, is acted upon by gravity. The second is of the elevator moving at a constant 2 meters per second. Acceleration is 0. In both cases, you have a constant acceleration situation. In both cases, you can use kinematics. I mentioned that there are common parameters. What are they? Well, the time that the bolt is in flight and the time that the floor moves, the distance we're interested in, that time of motion is the same in both cases. So that's a common parameter. And the bolt's coordinate and the floor's coordinate, when the two become 1, that will be a common parameter. So we're going to do both these problems. We're going to do them individually, and then we're going to combine them using those common parameters. I'm going to start with the elevator problem. So I've extended my sketch to show where the elevator ends up after the time interval that we're interested in, which is the amount of time it takes the bolt to come loose and end up hitting the floor. And during that time interval, the elevator's floor will move from y equal to 0 to some unknown coordinate, which I'm calling y hit. As was said earlier, the velocity is constant, the acceleration is 0, so the question arises, what kinematic relationship do we have that has coordinates associated with it, that has an initial velocity, that has time, and that has acceleration, which happens to be 0? Well, here we have it. This is the generic form. On your equation sheet, it probably says delta y equals v1t, etc. I prefer this form because with a delta y, you have to psych out whether the delta is positive or negative. In this case, all you have to do is just put in the individual coordinates, and the pluses and minuses take care of themselves. In any case, this variable right here essentially is asking you to identify what the coordinate is at the end of the time interval that you're looking at. Okay? So at the end of the time interval, the floor has risen to the coordinate y hit. That's what should go in this little bailiwick right here. As you can see, that's what I've written. This parameter right here is asking you to identify what the coordinate of the floor is at the beginning of the interval. At the beginning of the interval, it was at what I've called y1, so I'm putting y1, and proceeding in a like manner, we get ourselves down to this final relationship that relates the coordinate of the elevator's floor at the hit point to the time interval that the bolt was in flight. Now, you might wonder how you managed to go from a time interval that was obviously a time interval to a variable that looks like a single parameter in the same sense that y hit is a single coordinate. The magic lies in the consequence of a little mathematical trickery. Delta t is defined as the difference between the initial and the final time of the interval. If you start your stopwatch at the initial point, that value will be 0. If you define the final point in time as a variable t, then delta t simply equals t. What's important to note here is that y in this case is a specific coordinate. T in this case is actually denoting a time interval. Those are two different critters. And in fact, time is the only kinematic variable that you're going to deal with that isn't an instantaneous value. It's just something you need to know. In any case, during that same period of time, the bolt initially moves upward with a velocity of 2 meters per second. Then it moves downward under the influence of gravity. So what relationship do we have that has coordinates, initial velocity, acceleration, and time? Same relationship that we had before. Final coordinate of the bolt is y hit. So we write y hit. Initial coordinate of the bolt was what I've called on my coordinate axis y2. So I write y2. Which brings up kind of an interesting little problem. You will notice that I've got a y1 here, and in this spot I have a y2. What's going on? What you need to realize is that this is a generic relationship. Okay, this is telling you the general form of the kinematic equation. This variable effectively is telling you, go find out what the coordinate was at the end of the interval and put it in. Go find out what the coordinate was at the beginning of the interval, at time t1. Look on your coordinate axis, find that, and put it in. If on your coordinate axis you've defined that point as y2. That's what you put in. So these are generic variables. This is y at time t2. This is y at time t1. These are actual coordinates that have come off of your coordinate axis. Once again, two different critters. Continuing on, this is what the relationship looks like. And filling it in, y2 is 3, v0 is 2, a is minus 9.8. You end up with this final relationship. So we can put our two relationships together, and you will notice they both have y hit equaling something that is time dependent. Equating the two, you will notice you have two t's on both sides, which can be canceled. If you fuss, you come up with t is equal to 0.78 seconds. So apparently, the bolt free falls for 0.78 seconds, which means, according to the math, the elevator floor travels a distance 1.56 meters. And that's the solution we've been looking for. So what should your takeaway be for this problem? Temptation of a lot of students when they run into a hard problem is to go over it and over it and over it, and as a consequence end up pretty much memorizing it. That's not something you ought to be doing. What you should be trying to do is to understand how the problem was solved. If you can get the protocol down, you can pretty much take apart any kinematics-driven problem that you run into. And that's pretty much what you're shooting for. Anyway, that's it. Have a nice day.